the first problem, where we have a ring of mass capital M and radius A. This is a ring of mass capital M and radius A that lies on a smooth horizontal surface. The whole arrangement lies on a smooth horizontal surface like this. Okay. An insect of mass small m sitting on it starts crawling on the ring with a constant speed. So this is the center of the ring, and there is an insect I. There is an insect I of mass small m, and it starts moving with a constant speed v. It starts moving with a constant speed v along the ring, along the circumference. The trajectory of the center of the ring is what we want to figure out. The trajectory of the center of the ring is what we want to figure out. Now, a point representation of the ring alone, would be its center of mass. For the ring alone, what is its center of mass? The center of the ring, because of symmetry and because of uniformity, right? So the ring could be imagined to be a mass capital M placed at O, the center of the ring. Yes or no? Right? Now, to simplify matters here, what we do is the point mass capital M, which represents the ring, and a mass small m, which represents the insect, Now, when the insect attempts to crawl along the ring, are there any external forces acting on the insect? Yes. No. I mean, that gravity is acting like this, but it's balanced by normal reaction. Yes, there is frictional force between the ring and the insect, but then, if I look at the ring plus the insect, then do you perceive any external forces on a system comprising capital M and small m? No. On a system that comprises capital M plus small m, there are no external forces acting. Do you all understand this? Which means, on a system comprising capital M plus small m, if there are no external forces, the center of mass has no acceleration. The center of mass then has no acceleration. Yes or no? Right? The center of mass then has no acceleration. Now, if the center of mass has no acceleration, when the insect was at rest, the ring was at rest, what was the velocity of the center of mass? 0. Right? So the velocity of the center of mass at one instance was 0, and there was no acceleration on the center of mass. That means the velocity of the center of mass must remain constant. So it remains 0 at all times. Initially 0, no acceleration on the center of mass, and therefore it remains 0 at all times. Right? That means if the center of mass, even though capital M and small m both would be moving, their center of mass will not be moving. That means the center of mass of capital M and small m would be somewhere here at this point P, and it will remain at P. Yes or no? Yes, sir. Right? Now, for it to remain at P, first thing, let's say this length is A units. Let me locate the center of mass to begin with. This length is A units, right? The radius of the ring, right? And if this was x equal to 0, then this would be x equal to A, right? Then the x coordinate of the center of mass is going to be given by capital M into 0 plus small m into A divided by capital M plus small m. That would be the x coordinate of the center of mass, which is like small ma by capital M plus small m. Right? Yes or no? That means the center of mass is located at a distance small ma by capital M plus small m from capital M. Right? And from small m, this distance will turn out to be capital Ma by capital M plus small m. This is how we've completely and uniquely located the center of mass of this pair of particles. Right? Now, do you realize that if small m, this was small m, it moves to this position, and with respect to the line joining small m and capital M, if it has rotated by an angle theta, then do you realize that capital M must also rotate by the same angle theta? Why? Because if small m comes here, capital M must belong here, so that their center of mass remains at this position. Yes or no? Yes, sir. Right? Which means capital M, if this length was R1 and this length was R2, then capital M must be moving in a circle of radius R1 with center at this position. Small m must be moving in a circle of radius R2 with this as the center, so that the center of mass of capital M and small m remains at this location, So capital M, the center of the ring, will move in a circle of radius R1. What is R1? R1 is this. This is the trajectory of capital M. What's the trajectory of small m? The trajectory of small m would be a circle of radius R2, where R2 is this, with center at this center of mass. Yes or no? Right? Okay, do you all understand moment of a force, torque of a force, right? No? No, you no idea of, even in junior class never got center of torque, etc. 9, 10, moment of, you did ICSE, CBSE, okay. Okay, can I wipe this off? Can I wipe this off? Although at length I will handle it later, but for the time being, if a force F acts like this and its perpendicular distance from O, a point O, if the perpendicular distance from point O is L, let's say if F acts at a point P and the perpendicular distance of the line of action of the force from a certain point O be L, then this force F is known to produce a turning effect about O. The turning effect that it produces about O is called the moment of the force about O. Moment of the force about O is given by F into L. Product of the force into the perpendicular distance of the line of action of the force from the given point O. Now in this case, imagine this to be a rod, and if a force F acts like this and it was hinged at O, then this would produce a clockwise torque about O. So this force, say F1, will produce what's called a clockwise moment or a clockwise torque. About O. Say O was a hinge, and if there was a force F2 acting at a distance, say L prime from O, perpendicular distance L prime from O, then this force F2 about this hinge will produce a torque which is F2 into L prime, and this would be anti-clockwise. This is an anti-clockwise moment, anti-ACW, anti-clockwise moment about O. Because if this force were to be acting like this, imagine this to be a rod, it will want to rotate the rod in an anti-clockwise manner. Yes or no? Yes, sir. Right? Now, if F1 into L is more than F2 into L prime, then the whole thing would want to rotate clockwise. If F2 into L prime is more than F1 into L, then it would want to rotate anti-clockwise. If F1 into L is F2 into L prime, then we say that it would be in rotational equilibrium. It would be in rotational equilibrium. Right? We'll talk more about it. There are a bunch of mysteries associated with it, but not for the time being. We'll keep it pending for discussion later. Now, once you understand this business of a moment or torque about a certain point produced by a force, let's look at the next problem. Let's look at the next problem. Problem 2. A meter rule weighing 100 grams rests on a table with a part projecting over the edge. The length of the part projecting out, if a 5-gram body is hung at the end, just tilts the rule. So, say, this was the rule, and there was a 5-gram mass. There was a 5-gram mass overhanging like this, point P. The length of the part projecting out, if a 5-gram body hung at the end, just tilts the rule. So we want to find, in order that it could just tilt the rule, x units projecting out, the center of mass of the rule, which is 100 centimeters, would be 50 centimeters from here, right? Yes or no? Right? Now, in order, and from this point, you can imagine the entire weight to be acting. What is the weight? 100 grams. 100 grams to be acting like this, right? So then, this is proportional to the force also. 5 grams and 100 grams, that's proportional to the force also. Now, in order that it could just tilt about P, what is required is the torque of 5 about P must be just more than the torque of 100 grams about P. You know what I'm saying? See, this is the rod. It's as if there is 100 grams acting through its midpoint. There is 5 grams here, and there is this point P, the hinge, right? So in order that it could just tilt, this is x units. So this length would be 50 minus x units. X units. Now in order that it could just tilt about this point P, we must have 5 grams into x centimeters, just about greater than or equal to, limiting case equal to 100 grams into 50 minus x, in order that it could just tilt, right? So this would give us like x greater than or equal to 20 into 50 minus x, right? Or 21x greater than or equal to 1000, or x greater than or equal to 1000 by 21, which is 40 odd something, right? So x must be just slightly more than this amount for it to be able to tilt about the point P. That is what is required. Clear? No, you can't. That's the concept of torque only. That sabzi mandi is the concept of torque. That is why what they do is the two arms, they make them unequal. A dishonest shopkeeper in the sabzi mandi makes the two arms unequal. He makes sure that the arm where the weight would be put, that arm is longer, so that less weight would balance his 100 grams. That's the concept of torque only, dost. Okay.
And sir, when the center of mass of 100 gram and 5 gram was placed just at the end of that, then it
Sorry?
so कि 100 ग्राम और 5 ग्राम का center of mass just एज पे रहेगा, तब भी तो हो सकता है कि
नहीं होगा, because the torque of 500 grams would, the anti-clockwise torque of 100 grams would exceed the torque of that 5 grams about P, so it will not tilt.
center of mass दोनों का जो होगा वो just एज पे पहुंचेगा तब का.
वो एक ही चीज है, that's the same thing, that's the same thing. You're right. All right, problem 3. Two blocks of equal mass are tied with a light string which passes over a massless pulley as shown in the figure. Mass M, 60 degrees, this is 30 degrees. The magnitude of the acceleration of the center of mass of both the blocks is how much? That's what we want to find here, right? The acceleration of the center of mass of the two blocks. The magnitude of the acceleration of the center of mass. Now, one thing, there is mg sine 60 degrees acting this way. There is mg sine 30 degrees acting this way. There is mg cos 30 degrees and mg cos 60 degrees also, which is balanced by the normal reaction, so I'm not representing that here, right? Then there is tension T, tension T. Now, if I look at the two masses and the string as one unit, then tension would be deemed internal. It will require no further representation, right? So then the whole thing, since mg sine 60 degrees is more than mg sine 30 degrees, the whole thing will have an acceleration a like this, right? Which is given by what? If this will have an acceleration a this way, this will have an acceleration a this way, isn't it? So then the a would be given by mg sine 60 degrees minus mg sine 30 degrees divided by 2m. Yes or no? That will give me the common acceleration of the two masses along the plane. One down the plane, the other one up the plane. Right? And once you have this in place, m and m would get cancelled. Therefore, we have like a g by 2. Sine 60 degrees is root 3 by 2. That's the acceleration. Right? Now, the acceleration of the center of mass. The acceleration of the center of mass. Very simple, because okay, let me tell you. Okay, glad that you brought it up, but let me explain what this system could be equivalent to and why that is so. First, mentally you can imagine this to be straightened up. And I'll tell you why you could imagine that. That also I'll explain. I claim that the whole thing is like this actually. The reason I claim this is very simple. If I write the equation of motion for this, what would that be? The equation of motion for this, mg sine 60 degrees minus t is m into a. How about it? The equation of motion for this is t minus mg sine 30 degrees is m into a. Now I add the two equations. Let me add the two equations. If I add the two equations, then t will get cancelled and I get 2m into a is mg sine 60 degrees minus mg sine 30 degrees. Think of it now. Isn't it? You know what I'm saying? So it's as if there are two masses, m and m, like this. T is an internal force, will not appear. So that's an equivalent that you could spread out and deal with. Right? You don't have to write these two equations unnecessarily. You could spread it out and write your equations this way. The common acceleration, the net external force, this minus this, divided by 2m. This equivalence is sanguine. Fine? Okay. Now once we do this, can I remove this? Okay. Now it's as if, see, this is 90 degrees as all of you have seen, right? Let me call this the y direction and this the x direction. Right? Isn't it? So the acceleration of this mass a1, vectorially speaking, the acceleration of this mass, call it a1, is going to be what? A I cap. Vectorially, the acceleration of this mass a2 is going to be what? A j cap. Yes or no? Then the acceleration of the center of mass of the system is going to be what? M into a1 plus m into a2 divided by m plus m, that is 2m. That's the acceleration of the center of mass. Is it not? So which is like a1 plus a2 by 2. Right? That's the acceleration of the center of mass, which is to say that it's going to be a by 2 into I cap plus j cap. That's the acceleration of the center of mass vectorially. What we are seeking is, where a is known from those considerations, what we are seeking is magnitude of the acceleration of the center of mass is what we are seeking, which is going to be the magnitude of this vector. The magnitude of I plus j is root 2, isn't it? The magnitude of I cap plus j cap is root 2. So this is like a by 2 root 2. A by 2 root 2 would be the magnitude of the acceleration of the center of mass. Right? So a is known. This by 2 into root 2 will give you, that means this by root 2 will give you the acceleration of the center, magnitude of the acceleration of the center of mass. Is that fine or not fine? Simple, right? Confused? Where? See, the calculation of a was understood. Now the acceleration of this vectorially would be a into I cap, and of this would be a into j cap, right? So acceleration of the center of mass is what? m1 a1 plus m2 a2 by m1 plus m2, which gives me this. Now what we are seeking is magnitude of the acceleration of this. Would be magnitude of this vector, which is a by 2. The magnitude of I cap plus j cap is root 2, isn't it? That's it. Magnitude of the acceleration of a by 2 root 2, where a has already been obtained. So plug in the value of a from here and you get the magnitude of the acceleration of the center of mass. How about this? Is that okay or not okay? Very good. Let's look at the next problem. So far so good, right? Problem 4. We have 4 masses at the vertices of a square. 4 masses m1, m2, m3, m4 at the vertices of a square. M1 which is 2m, M2 which is 4m, M3 which is m, and M4 which is at this vertex. We want to be able to find the value of M4 so that the center of mass of all the 4 particles is at the center of the square, right? Now think of it. Look at M1 and M3 first, right? Essentially, I could find the center of mass of 2m and m, and I could find the center of mass of m4 and m2. And if both have their center of mass at certain locations, then the center of mass of those 2 locations would be the center of mass of the square, isn't it? Now, say this is A, B, C, D. Along AC, where does the center of mass of M1 and M lie? Do you realize that it will lie at a certain point P1 here? Closer to 2M, the center of mass will show proclivity towards a heavier mass. It will be always closer to a heavier distribution, right? So this 2m and m could be replaced by a 3m at P1, could be replaced by a mass 3m at P1, the center of mass of 2m and m, yes or no?
Yes, sir.
Right. And the center of mass of M4 and M2, now depending on what M4 is, it would either lie here in this region. See, suppose M4 was bigger than M2. Suppose M4 was bigger than M2. Then the center of mass of M4 and M2 would be closer to M4, right? It will lie somewhere here. Now in which case, that means the center of mass of the system will lie along P1, P2. So that means M4 can't be bigger than M2, right? Second possibility, right? M4 therefore cannot be bigger than M2. Very good. Now suppose M4 was smaller than M2, then the center of mass of M4 and M2 would lie somewhere here, in which case the center of mass of the system would lie somewhere here, which again does not include the center of the square. Not possible. Suppose M4 was equal to M2. Suppose M4 was equal to M2. Then the center of mass of M4 and M2 would lie somewhere here, P2. Now the center of mass of the system will lie somewhere here. That means for no value of M4 can you have the center of mass of this unit at the geometrical center. We cannot find a value of M4 for which the center of mass of the unit is at the intersection of the diagonals. Have you registered this thought or not?
Yes, sir.
Suppose M4 was larger than M2, then the center of mass of M4 and M2 would be somewhere here, in which case the center of mass of the system would be along the line joining P1 and P2, which is not what we want. We want the center of mass to be here. Suppose M2 was bigger than M4, then the center of mass of M4 and M2 would be somewhere here. Nahin. And then the center of mass of the system would be along this. That also is not acceptable because we want the center of mass to be here. Suppose M4 was equal to M2, then the center of mass of M4 and M2 would be here, halfway, in which case the center of mass of these two will lie somewhere here, which again is not desired. Therefore you cannot find a value of M4 in this case for which the center of mass lies at the geometrical center. Are you okay with this or not okay? Okay with this?
Sir, ऐसे भी तो कर सकते थे M1 और M3 को x coordinately और
Right, perfect. Good.
will come different.
Absolutely. You could have done that. Fine. 5. A rope thrown over a pulley has a ladder. This is a pulley. Has a ladder at one end. This is the ladder at one end, with a man of mass small m on one of its ends. Let's say this is the man of mass small m. Hands, huh? I'll just show his hands. He's connected to the ladder. If you don't like it this way, very close to the ladder, like this. He's holding on to the ladder, right? Man of mass small m. And a counterbalancing mass capital M at the other end. A counterbalancing mass capital M at the other end. Counterbalancing mass capital M at the other end. The man climbs with a velocity Vr relative to the ladder. The man climbs with a velocity Vr relative to the ladder. He climbs with a velocity Vr. Ignoring the masses of the pulley and the rope, as well as the friction on the pulley axis, the velocity of the center of mass of the system is what we are seeking. First of all, look, when the man was not attempting to climb up the ladder, this was a counterbalancing mass. Means it was keeping the whole thing in equilibrium. That means if you saw a mass capital M here, then you must see a total mass capital M here, so that it's counterbalanced. Therefore, if the mass of the man is small m, the mass of the ladder must have been capital M minus small m must have been the mass of the ladder, right? So the ladder must have been of mass capital M minus small m. Must have been the mass of the ladder. Right? Now, let's say when he attempts to climb with respect to the ladder with a velocity Vr. Okay. Say this mass m moves up with a velocity V0. This mass m moves up with a velocity V0. And therefore, the ladder will move down with a velocity V0 to maintain the string length constant. The ladder, a rigid entity, would move down with a velocity V0 downwards. Now, what's the velocity of the man then, as seen? With respect to the ladder, it's Vr. But the absolute velocity of the ladder would be what? Vr minus V0 would be the absolute velocity of the man, not the ladder, would be the absolute velocity of the man. Therefore, the man small m has a velocity not Vr, but would be Vr minus V0 would be the velocity of the man. Yes or no? Now, let me calculate V0. Look, the physics involved in the problem is as follows. On this mass capital M, there is mg acting this way and there is T acting this way on capital M, right? On this ladder man combination, there is total capital mg acting this way and there is tension T acting this way. Yes or no? Right? Now, one thing, in a small time delta t, the impulse of tension acting on capital M must be the same as impulse, or the net vertical impulse acting on this must be the same as the net vertical impulse acting on this. Why? Because in a small time delta t, what's the impulse that upward impulse that acts on this? T minus mg into delta t is the vertical impulse that acts on this. isn't it? In the same time, on the ladder-man combination, what's the vertical impulse acting? T minus mg into delta t is the vertical impulse acting on this. Yes or no? That means the vertical impulse acting on the unit to the left must be the same as the vertical impulse acting on the unit to the right. That means if the same vertical impulse acts on it, that means the gain in linear momentum of this must be the same as the gain in linear momentum of this. Yes or no? Yes, impulse means what? Change in linear momentum, no? So if the same impulse acts on the two, then it must come with the same change in linear momentum on the two sides, isn't it? The linear momentum change brought about on the two sides must be the same. The vertical linear momentum gained by this must be the same as the vertical linear momentum gained by this. Yes or no? Because what brings about a change in linear momentum of this? T minus mg acting for delta t. What brings about a change in linear momentum of this? T minus mg into delta t. And t and mg are the same. Therefore, they're talking about the same change of linear momentum on both sides. Yes or no? No? I'll repeat, of course, any number of times. I'm saying, have I told you what impulse is in the past? Impulse is force into delta t, right? Which is actually change in linear momentum, right? So this mass is acted upon by these two forces. So this force acting for delta t, that's a change in linear momentum of this. This is the upward change in linear momentum of this mass. The net force acting on this is T minus mg into delta t. That's a vertical change in linear momentum of this. So same change in linear momentum of both the masses in the upward direction, right? Now, what's it? This is mv naught, therefore it gains a linear momentum mv naught, and that must be the gain in linear momentum of this, which is m into Vr minus V naught plus capital M minus M naught minus capital M minus M naught into V naught. Yes or no? What's the linear momentum of this system? Upwards. Small m into Vr minus V naught minus capital M minus M into V naught. Minus, right? This is downwards. Minus capital M minus small m into V naught. Yes or no? Yes. Okay. Now once you understand this, see, we have minus mv naught plus mv naught getting cancelled, and mv naught minus mv naught, that is 2 mv naught on the left hand side, that must be equal to m plus m into Vr, right? So this gives me V naught that we were looking for as m into Vr divided by 2m. Yes or no? Will you now be able to calculate the velocity of the center of mass of the system? How do you calculate the velocity of the center of mass of the system? Essentially, it's going to be m into Vr minus V naught, right? M into Vr minus V naught for this velocity, m into velocity of this minus capital M into velocity of this plus, I'm sorry, capital M minus small m into velocity of this plus capital M into V naught divided by the total mass 2m. That's the velocity of the center of mass of this unit. Hey, but look, this minus this was actually 2m, was mv naught, isn't it? This minus this was actually capital mv naught. So what I can do is, just to simplify matters here, this part is actually capital mv naught. Refer to that equation. Refer to this equation. right? So this is capital MV naught plus capital MV naught. 2m V naught divided by 2m, that makes it V naught. That's the velocity of the center of mass, V naught, which we have already calculated. That's the velocity of the center of mass, isn't it?
सर अगर नीचे डाउनवर्ड डायरेक्शन से पॉजिटिव
कोई फर्क नहीं पड़ता, not make any difference. Huh?
मेरा आंसर माइनस में आता है नीचे मॉड
Right? Six is very simple. Can I skip this? Right? I mean, impulse will be change in linear momentum. You can find the velocity at that instant of time and change in linear momentum. That will be the impulse of the force acting. Problem 7. Two particles of equal mass have velocities this is V1 equal to 2 I cap meters per second, this is V2 equal to 2 J cap meters per second. The first particle has an acceleration A1 given by 3 I cap plus 3 J cap meters per second squared, whereas the acceleration of the second particle is 0. We want to figure out the trajectory of the center of mass of this unit. We want to figure out the trajectory of the center of mass of this unit. First of all, let me find out the velocity of the center of mass at this instant. m1 v1 plus m2 v2 by m1 plus m2. But m1 and m2 are equal, so velocity of the center of mass would be v1 plus v2 by 2. Because m1 equal to m2, right? So velocity of the center of mass is simply going to be v1 plus v2 by 2. That makes it I cap plus j cap meters per second is the velocity of the center of mass of this unit at this instant, right? The acceleration of the center of mass is going to be m1a1 plus m2a2 by m1 plus m2, but again m1 equal to m2, so it's simply going to be a1 plus a2 by 2. Which is like 3 by 2 I cap plus j cap. So far so good, right? Yes. Now notice this. The velocity of the center of mass is I cap plus j cap. The acceleration of the center of mass is 3 by 2 I cap plus j cap, and therefore the velocity of the center of mass is parallel to the acceleration of the center of mass. Yes, isn't it? The acceleration of the center of mass is this way. The velocity of the center of mass is also this way. Right? Isn't it? Are these two vectors not parallel to each other? They differ only by a scalar 3 by 2. They are parallel vectors. So if ACM is parallel to VCM, then the path that it would undertake is a straight line. It will take up a straight line path. Straight line trajectory. Make sense, right? No? Time to proceed? Problem 8. A particle of mass 2m is projected at an angle of 45 degrees with the horizontal with a velocity of 20 root 2 meters per second. A particle of mass 2m projected with a velocity u equal to 20 root 2 meters per second at an angle of 45 degrees. After 1 second, there is an explosion. At t equal to 1 second. See, first of all, what's the x component of this velocity? 20 root 2 cos 45 degrees. That is 20 meters per second is the initial ux, and the initial uy is what? 20 root 2 sine 45 degrees, which is also 20 meters per second. Right? One second later, what happens to ux at t equal to 1 second? At t equal to 1 second, ux remains 1 meter per second. What happens to uy? Uy say becomes vy, which is 20 meters per second, 20 meters per second. What happens to vy? That's initial vy, which is 20 minus 10 into 1, that is 10 meters per second. 1 second later, bless you. Right? That means 1 second later, it has a velocity, in the combined mass has a velocity of 10 meters per second vertically and has a horizontal velocity of 20 meters per second. Right? That's the 2m. And the height, what would be the height that it would have gone up? H naught would be vyt minus half gt squared. Vy, initial vy is 20 into t minus half of 10 into t squared, which is 15 meters. Right? Now, at this point, there is an explosion. At this point, there is an explosion, and this results in two equal pieces, each of mass small m. Each of mass small m. One particle comes to rest. There is particle m which comes to rest. It breaks up into 2m breaks up into m and m. One comes to rest. The other one now, I claim, will have, the other m now will have a velocity 20 meters per second like this and 40 meters per second like this. Realize that? To preserve linear momentum in the x and the y direction. Now this has given up all its linear momentum. So that means the linear momentum of the other one must have doubled so that the same linear momentum is preserved for the unit, isn't it? Right? So this mass, the other mass, has an upward velocity of 20 meters per second and has a velocity of, horizontal velocity of 40 meters per second. Therefore, the h max reached by this particle above this point, above O, the maximum height that it will attain is 20 squared by 2g. That makes it 20 meters. That makes it 20 meters. That's the maximum height that this attains from this point onwards. Right? That means it had already gone 15 meters. Now it will go further 20 meters. That means it will attain a maximum height of 35 meters. It will attain a maximum height of 35 meters. What do you say? Right? This one? Vy? V is u plus at in the y direction. Initial velocity in the y direction is 20 meters per second. Minus a is minus g into t. 1 second later, the velocity in the y direction will, therefore, I'll apply v equal to u plus at in the y direction. U is 20, a is minus g, t is 1. So velocity in the y direction 1 second later would be 10 meters per second for the mass 2m. Got me now? This is the state of the mass 2m 1 second later, just before explosion. Just after explosion, this must be the state. This comes to rest, whereas this, its vertical velocity would have got doubled because mass has become half, so velocity must have become twice. Right now? Proceed. particles, mass small m small m. Velocities v1 and v2 at angles of theta 1 and theta 2. Now, they have a center of mass somewhere here, right? And let's say this is the x direction and say this is the y direction, right? The center of mass in the x direction has a velocity which is what? M into v1 cos theta 1 minus m into v2 cos theta 2 divided by 2m. That's the velocity of the center of mass in the x direction, right? Which is like a v1 cos theta 1 minus v2 cos theta 2 divided by 2. That's the velocity of the center of mass in the x direction. The velocity of the center of mass in the y direction is going to be m into v1 sin theta 1 plus m into v2 sin theta 2 divided by m plus m, which is like a v1 sin theta 1 plus v2 sin theta 2 divided by 2, right? Isn't it? So the center of mass then has a velocity vx and has a velocity vy at this instant of time, right? And is subject to gravity this way, right? Now realize that there is a prospect of VCM in the x direction becoming 0. That could be 0, isn't it? It's possible that v1 cos theta 1 minus v2 cos theta 2 be 0. That's a possibility. We could choose v1, v2, theta 1, theta 2 such that the numerator of this could become 0, right? That could happen, right? If VCM in the x direction is not 0, that means if this is not 0, Vy is anyways not 0, Vy is anyways not 0, then this would represent a projectile trajectory, parabolic trajectory. It has a non-zero horizontal velocity, non-zero vertical velocity. Subject to g downwards, it will take up a parabolic trajectory, regular projectile motion, right? However, if VCM in the x direction be 0, that means if this is 0, that means it only has a vertical velocity Vy and subject to g downwards, that's the state of the center of mass at the instant of launch, and under the influence of g with the initial velocity just opposing g, it will only move upwards, it will only move along a straight line and vertically upwards. That would be the path taken up by the center of mass. If v1 cos theta 1 is v2 cos theta 2, then the path of the center of mass will be a straight line. Otherwise, in all other cases, it's going to be a parabola. It's going to be a parabola. A system of two blocks, A and B, and a wedge C is released from rest. The masses of the blocks and the wedge are m, 2m and 2m. M, 2m and 2m.
the displacement of the wedge C when block B slides down a distance of, this is block A, this is block B, this is the wedge C. When this slides down a distance of 10 centimeters, we want to find the displacement of the wedge C when block C slides down the plane a distance of 10 centimeters. Okay. Now, look, when this slides down 10 centimeters along the plane, imagine everything to be at rest. Imagine C to be not moving. Imagine C to be not moving to begin with. Then, in this direction, its displacement, this is 45 degrees, right? So, 10 cos 45 degrees, 10 by root 2 must have been its horizontal displacement, 10 cos 45 degrees, right? Okay. Now, this block A then would have moved up 10 centimeters,
Yes, sir.
right? And the horizontal displacement of block A, then this is also 45 degrees, would have been 10 by root 2, 10 cos 45 degrees. Yes or no? Right. Now, 1. In a system that comprises A, B and C, in a system that comprises A, B and C, can you perceive any force in the x direction? Suppose this is the x direction. What is an external force in the x direction on the system that comprises A, B and C? Nothing. No external force acting in the x direction on the system that comprises A, B and C, right? That means if this is 0, that means the center of mass of the system in the x direction must have 0 acceleration, right? Now, at the time it was just released, the velocities of all the 3 entities was 0. So, the velocity of the center of mass at that instant was 0. And since there is no acceleration in the x direction, in the x direction the velocity of the center of mass must remain 0. Yes or no? Now, when this moves to the right by an amount 10 root 2 and this moves to the right by an amount 10 root 2, they disturb the x coordinate of the center of mass of the system, right? The block allows that to happen to begin with. And the extent to which the disturbance takes place is m into the disturbance 10 by root 2, m into 10 by root 2 plus 2m into 10 by root 2, right? Yes or no? Now, they have caused this disturbance. Now the blocks come to rest. Now the two masses along with the block move by an amount x to the left. Total mass that moves to the left by an amount x is 5m, 4m plus m, 5m moves by an amount x to the left to restore the x coordinate of the center of mass of the system. Realize the same raft boat problem, right? See, the disturbance caused to the right is m into 10 by root 2 by this, mixi is the disturbance. And the disturbance caused by this is 2m into 10 by root 2 by this. Now, all along, C allowed this disturbance to happen, allowed the center of mass to get shifted to the right. Now, the masses come to rest and the total mass 5m moves by an amount x to the left so that it can restore the x coordinate of the center of mass of this. And why should the x coordinate of the center of mass remain same? Because the center of mass has no velocity in the x direction, so its x coordinate is not changing, right? And therefore, this will give you the amount by which the wedge must move to the left, x left, right? Got the answer? Right. Let's look at 11. Then it would have not, x coordinate would not have remained preserved. Then you would conserve linear momentum in the x direction. That is what you would do, right? The
Next problem. Problem 11. There is a smooth spherical shell. There is a smooth spherical shell of radius 6r and of mass 4m and of mass 4m, right? The small sphere has radius small r. This is a small sphere which is right here, has radius r and has mass small m, right? The arrangement is placed on a smooth horizontal table. The arrangement is placed on a smooth horizontal table. The small sphere is now released, is let go. The x coordinate of the center of the shell when the small sphere reaches the other extreme positions. That means now this will go this way, and after a while the small sphere will go this way, say from C1 to C2. The center C, which is that of the bigger sphere, we want to find by what amount should this move to the right in order by the time this comes here. Hey, look, again, no external forces in the x direction. Acceleration of the center of mass in the center of mass of small m n, that means capital M n 4m is 0. Velocity, initial velocity is 0, and therefore it remains 0 because there is no acceleration in the x direction. That means the x coordinate of the center of mass of the system must remain constant. I'll explain. See, this causes a disturbance to the left. So to neutralize that disturbance, it must move to the right, isn't it? MIXI will have to remain preserved. So when this goes there, see, this total length is 12r. This total length is 12r, isn't it? Whereas take away 2r from this. So that means effectively the small sphere has moved by an amount 10r. Has moved 10r. That means by what amount has the small sphere disturbed the whole thing? M into 10r leftwards. To neutralize that change, this along with the whole thing, that means 4m plus m, 5m must move by an amount x naught to the right. So this must be 5m into x naught to the right. So x naught will be 2r, right? It's the same concept, the one that we did in, see, taking care of disturbances, superimposing disturbances, that's what we do. Although the whole process is happening simultaneously, we imagine that this one independently moves to this without the sphere moving, and then the sphere along with this moves to the right by an amount x naught, so that MIXI remains the same. See, m into 10r, this is moved by an amount 10r leftwards. So then the total mass 4m plus m, 5m moves by an amount x naught to the right. So x naught must be 2r. Is that okay? Problem 13. There is a 2 kg block here. There is a 1 kg block here. Passes over a light frictionless pulley. The masses are initially held at rest at the same horizontal level and then released. We want to find the distance traversed by the center of mass 2 seconds subsequent to the release. Right? Hey, one thing. Can I now say that the acceleration of A downwards, same consideration, will be 2g minus g divided by 3. Now I can straighten it up and do the same thing that I did earlier. That will be the acceleration, that is g by 3 will be the acceleration of this downwards, and would be the acceleration of this upwards, right? And therefore the center of mass, acceleration of the center of mass would be, let's say, 2 into g by 3 minus 1 into g by 3 divided by 3. Yes or no? That means g by 9 would be the acceleration downwards of the center of mass, right? That would be the downward acceleration of the center of mass, right? Therefore the distance traveled by the center of mass in how many 2 seconds would be half of ACM into t squared. T is 2 seconds, ACM is this. Plug in to calculate the vertical displacement downwards of the center of mass of the unit. Got me kya? Let's look at 14. Okay, if you don't like all of this, T 2G. 2G minus T is 2A if you want it this way. I didn't want to do it this way, but this is what you like, it seems. So, and then this one would be T minus mg is 1 into A. If you add the two, then A is, but what I said was straighten it up. This has a 2g acting this way, that has a g acting that way. 2g minus g is the net force divided by the total mass. That's the acceleration of the system. Just mentally imagine it to be straightened like I did earlier, right? Sounds fair? A man of mass 80 kgs is riding on a small cart of mass 40 kgs. God, imagine. (40 kgs), 80 kgs. Which is rolling in this direction with a velocity of 2 meters per second. He is running on the cart so that his relative velocity is 3 meters opposite to the motion of the cart. That means his relative velocity is 2 meters per second, is 3 meters per second in the opposite direction. That's given, right? What is the speed of the center of mass of the system? Now, what is the absolute velocity of the man in this direction? 3 minus 2, which is 1 meter per second. That's the velocity of capital M. The velocity of small m is 2 meters per second. So the velocity of the center of mass of the system, taking leftward positive, rightward negative, would be capital M into 1, 80 into 1, and then minus small m into V naught, that means minus 40 into 2, divided by 120, which is 0. Velocity of the center of mass of the man plus cart is 0, right? That means the x coordinate of their center of mass remains the same, right? Can I wipe this off? Problem 15, your attention please. A body of mass 60 kgs is standing over a platform of mass 40 kgs.
he throws a 1 kg stone with a velocity of 10 meters per second. At an angle of 45 degrees with respect to the ground. The displacement of the platform on the horizontal surface when the stone lands on the ground. When the stone lands on the ground. Hey, when the stone lands somewhere here on the ground, that means it covers its range u squared sine 2 theta by g. When the stone lands somewhere on the ground, that means it covers a range which is u squared sine 90 degrees by g. U squared means, therefore that makes it 10 meters. That makes it 10 meters, right? Now very simple. The stone has disturbed the MIXI. The mass of the stone is given to be 1 kg. Mass of the stone is given to be 1 kg. It has disturbed the MIXI by what amount? 1 mass into the range are 10 meters. That's the extent to which it has disturbed the MIXI. To restore the MIXI, now 60 plus 40, that means 100 kgs moves by an amount x naught to the left to restore the x coordinate of the center of mass. So x naught would be 0.1 meters or 10 centimeters. Right? So the platform moves leftwards to restore the x coordinate of the center of mass by an amount 10 centimeters. Clear? Hey, this surface has friction, is rough. This mass, when it moves down, as we have seen earlier, this would have a tendency to move leftwards. Recall that from our earlier discussions? The wedge would have a tendency to move leftwards, right? Now, friction therefore, static or kinetic, would act rightwards. Friction on the wedge will act rightwards. Do you then realize that this is the only external horizontal force acting on the system comprising capital M and small m? Is this not the only external horizontal force acting on the system comprising capital M and small m?
Yes.
Yes. And the effect of this rightward force would be that the center of mass would move only to the right. Can the center of mass ever move to the left? The net of external forces is perceived by one common particle. What particle is that? The center of mass particle. That's the premise on which we define center of mass. So if the net of all external forces is acting in the x direction, the center of mass will move in the x direction only, will get accelerated in the x direction only. Right? So in this case, if there is, do you realize that? Therefore, if at all the center of mass will move to the right, the center of mass can never move to the left. The center of mass can never move to the left. There is no possibility for the center of mass to move to the left, because the net of all horizontal forces is small f to the right. Be it static friction or kinetic friction, does not matter. Right? All right, there is a string here on a horizontal surface, and there are two particles A and B like this. There is a particle A of mass small m, and there is a particle B of mass small m. And the total length of the string is 2L. This length is given to be L, whereas this entire length of the string, capital L naught, is 2L. Is the total length of the string, 2L. Right? The particle at end B is imparted a velocity u perpendicular to AB. Perpendicular to AB, it's imparted a velocity u. Velocity of A just after the jerk. Now see what is going to happen. the string is initially in the collapse state. This is the collapse state of the string. It's not taut, right? When this particle is given a velocity to the right initially, there would be no tension built up. In a collapse state, there would be no tension in the string. And if there is no tension in the string, particle A will stay neutral about changes taking place with B, right? Particle A will not respond, because the only way it could communicate with B is by means of tension in the string, which is absent because the string is in a collapse state, right? However, when this keeps moving to the right, the string starts to straighten. It starts to straighten. Yes or no? Eventually, you would find a state where the string has completely straightened, and the direct distance between A and B is the length of the string, which is 2L. Yes or no? Right. Now at this instant, just before straightening up completely, right, the mass B has a velocity u to the right. The mass B has a velocity u to the right. Clear? Now, when the string straightens, just after this, the string is going to straighten up. When the string straightens, there would be tension built up in the string. There would be tension built up in the string. That tension will act on A in this direction, will act on B in this direction, right? But now, right after the string straightens, I claim that along the string, the velocities of A and B along the string should become the same. If they don't, the string is not straightened, isn't it? At the end of the string, the two particles if the string is in a state of tension, then at the end of the string, the velocities of the two particles along the string length must be the same. That's a string constraint, isn't it? Right? That means the velocity of this along the string would be B, and the velocity of this along the string would be V. Yes or no? However, this one, just before straightening, completely straightening, now this is B, this length was L, this is theta. Realize that sine theta is half. See, sine theta is half, theta must be 30 degrees. Theta therefore must be 30 degrees, right? So then look at this theta. Now, this particle B has a velocity u sine theta like this, u sine 30 degrees like this, and u cos 30 degrees like this just before it straightens. Just before it straightens, the velocity of B along the string and perpendicular to the string is u sine 30 degrees and u cos 30 degrees as shown, right? Now, when there is tension T acting, so right after this, the tension builds up, right? That's a state of jerk. That's a state of jerk. The string suddenly jerks. When it straightens, it jerks. There is a sudden build-up of tension from a collapsed state to a taut state. There is build-up of tension. The string experiences a jerk. That tension T, which is a measure of the jerk, will change the velocity of this, will change the velocity of this. This T will increase the velocity of this. This T will decrease u cos 30 degrees. But to such a degree that their final velocities in this direction will remain the same. But will this T change u sine 30 degrees? No, because it's perpendicular to u sine 30 degrees. That means that T will not change this u sine 30 degrees. That T will only bring A and B to a common velocity along the string. Yes or no? Right? Now, just before completely straightening, just before the jerk, along the string, what was the linear momentum of the system? Mu cos 30 degrees. Just before straightening, the linear momentum along the string was mu cos 30 degrees. Hey, if you look at this particle system, right, then A and B, along with the string, you don't find any external force along the length. Do you find any external force along the string length AB? That means the total linear momentum along the string length must be constant. Just before completely straightening, they had a linear momentum mu cos 30 degrees. Right after it straightened, mv plus mv, that makes it 2mv. Right now. Got me? So then V becomes computable from this, because U is given, U cos 30 degrees by 2, U root 3 by 4. V becomes U root 3, conserving linear momentum along the string length AB for the two particle and the string system, because there are no external forces acting on the pair along the length AB. Weber? Got me? Nahin? Sure na? So V then is U root 3 by 4. Prince, got me?
Sir, can you please explain why the velocities will be same?
See, the pulley thing, fixed pulley. If this has a velocity 3 meters per second along the string length, then this must have a velocity 3 meters per second along the string length. If they had different velocities along the string length, then the string length will change, isn't it? Then the string length will change. But the string is an inextensible body, isn't it? Suppose this had a velocity 5 meters per second and this had a velocity 2 meters per second. Then every second the string length will increase by 3 meters per second. But is that happening? Like a string. No, then it will be a spring. Then it will not be a string. The string is an inextensible body. The velocities at the end of the string of the two entities in this case will remain the same to preserve the string length. To preserve the string length, isn't it? Got me now? So far so good? Very good. All right. So we have particle of mass small m. This is a particle of mass small m moving with a speed v, and then eventually colliding with 2m, which is initially at rest, circular tube of radius r, center O, perfectly elastically. I want to find after collision the time it will take to collide again. If it's a perfectly elastic collision, see, what's the relative velocity of approach? Magnitude of relative velocity of approach, v. In a perfectly elastic collision, velocity of approach must be the same as velocity of separation. So the velocity, relative velocity of separation, relative velocity of approach, relative velocity of separation, it should also be v in magnitude. Yes or no? That means after collision, this has a velocity v with respect to this, right? Isn't it? After collision, suppose small m has a velocity v1 and 2m has a velocity v2 right after collision, has a velocity v2, then do you realize that v2 minus v1 must be v? Relative velocity of separation must be relative velocity of approach, right? So which means it's equivalent to saying that it's as if small m is at rest and it's as if 2m is moving with a relative velocity v, isn't it? In a relative velocity situation, you can fix one particle and cause the other particle to move with the relative velocity, right? So it's as if 2m moves with a velocity v and small m is at rest, right? Therefore now the time that it will take to hit again would be 2 pi r by v. isn't it? Time that it will hit small m again would be relative separation between them is 2 pi r divided by the relative velocity, which is v, isn't it? That's the time it will take for them to collide subsequently. Is that okay? So we have a mass 2m harmlessly resting on a horizontal surface, and the string is not taut right now. Realize that it's folded and this mass m is moved up. This is the folded state of the string, right? This length is h, and then this mass m is released vertically. When it drops through a distance h, it will become taut. When it drops through a distance h, it will become taut, isn't it? And when it does become taut, this would have, that means just before the string becomes taut, it has a velocity v equal to root 2 gh, right? And this is at rest just before straightening, just before completely straightening, it has a velocity root 2 gh. Now, right after this, there is built-up of tension in the string. There is an impulse. Because of the tension in the string, there is an impulse. That impulse is j. That means tension into time is the impulse. Tension into time is the impulse. This is the mass 2m. And that same impulse, t into delta t, would act on this mass, right? Now, the string is in a state of tension now. This will therefore acquire a velocity v naught like this, and this will acquire a velocity v naught like this. Right after straightening, the two ends will acquire the same speed, yes or no? That's string constraint. That's just restating string constraints, right? Now, look, as far as this mass is concerned, right? The only impulse acting on it is j. Let's say the net impulse acting on it is j, right? J, therefore, must be change in linear momentum in this direction, which is 2m v naught, right? Now, this originally had a velocity v like that, right? But after the impulse, its velocity changed to v naught in a short time. Therefore, the impulse acting on this is final linear momentum in the direction of impulse minus initial linear momentum in the direction of impulse. Impulse would be final linear momentum in the direction of impulse minus initial linear momentum in the direction of impulse. Final linear momentum in the direction of impulse is minus mv naught minus initial linear momentum in the direction of impulse, which is minus mv. That's a change in linear momentum in the direction of impulse, yes or no? And this will give you v naught. V naught, as you can see, then would be v by 3. V is root 2 gh.